Hello, hello, hello. In this worked example, we're going to think about escaping to Mars, taking a trip from Earth to Mars. A lot of people are thinking about this. It used to be science fiction, but now, well, we're routinely sending robotic craft from Earth to Mars, Perseverance most recently, but people are beginning to think seriously about humans traveling to Mars. SpaceX. Elon Musk's company is pretty serious about setting up colonies on Mars in the not too distant future. Maybe someday some of you will travel to Mars. But what I'd like to do in this worked example is use some of our theory about energy and changes in potential energy due to gravity and begin to think about some of the energetics involved in traveling from Earth to Mars. So here's a fairly realistic to scale, well, not totally to scale, but it's a drawing of what a sort of bird's eye view looks like of our solar system. Here's our sun here right in the center, and the Earth orbits around the sun in a fairly circular orbit, and then Mars is orbit is a little bit more elliptical. And this is sort of what it looks like. And we want to think about what it takes to get from here to here, but be mindful of the fact that these are not stationary objects. They're each orbiting around the sun. The Earth goes around its orbit in 365 days, as you know. And the Martian year is longer for reasons Kepler's third law has a lot which we'll study soon, will tell us exactly how to calculate how long it takes for Mars to go around. But the answer turns out to be uh, almost twice of an Earth year, 687 Earth days for Mars to make one complete revolution. So anyway, we want to think about launching a rocket from the Earth to Mars. So let's dig in. So let's start by writing down some numbers, some distances here. So the distance from the Sun to the Earth, which we'll call R S sub SE, the distance from the Sun to the Earth, is about 1.5 times 10 to the 11th meters. The distance from the sun to Mars, well, it's a little bit less well defined because, as we said, Mars's orbit is elliptical. But as an average distance, the average sort of distance that Mars is from the sun is about 2.3 times 10 to the 11th meters. And a couple of other relevant numbers. The mass of the sun, which we'll call m sub s, is about 2 times 10 to the 30th kilograms. And the mass of the Earth, obviously a lot less, is about 6 times 10 to the 24th kilograms. And let's also list the mass of Mars, which we'll call m sub m. Mars is about a tenth the mass of Earth, so only 6 times 10 to the 23 kilograms, very roughly. Okay, so let's start off with what I'll call the classic escape velocity situation, which is a version of which is done in the Wolfson textbook, or just about every introductory physics textbook that's ever been written does this problem. So the problem is you've got a rocket and you're going to launch it from the Earth. So it's going to start out at the surface of the Earth and it's going to accelerate very quickly. It burns most of its fuel within 50 miles or so of the Earth's surface. So basically, the strategy is you give it enough initial velocity at the start, and then you let just gravity act on it. And when we talk about escape, we want to give it enough initial speed so that as it moves farther from the Earth and the gravitational force of the Earth is tending to slow it down, if it has enough speed, it will make it all the way out to infinity and beyond, as they say in the movies. So how does that calculation go? Well, we're going to make use of the fact that after the rocket engine shuts off, the system in this story just consists of the rocket and the Earth, and it's an isolated system. So the total energy of the system is conserved, and the energy changes are due to changes in the gravitational potential energy of the Earth rocket system and the kinetic energy of the rocket, basically. That's where all the kinetic energy in this problem lies. And that's got to add, the changes have got to add to zero because it's an isolated system. And now we're going to make use of the correct way to calculate changes in gravitational potential energy, which, as you now know, would be written for the system of the Earth and the rocket, just in general. It's this universal constant g times the mass of the Earth times the mass of the rocket. And then we have to multiply it by 1 over the initial distance that the rocket is from the Earth's center minus 1 over the final distance that the rocket is from the Earth's center. And if we're talking about this escape problem, we're going to assume that the rocket is going to make it out all the way to infinity. That means that RF is going to be infinity, and that means that we can ignore this term here. That's going to go away. And not only that, but we're going to assume that we start right on the Earth, right near the Earth's surface. So Ri is going to be just the radius of the Earth. So for a rocket starting at the surface of the Earth and making it to infinity, the change in potential energy, which will be, of course, an increase in potential energy, is just given by g times the mass of the Earth times the mass of the rocket divided by the radius of the Earth. And in this problem, the change in kinetic energy of the rocket, that's just equal to the final kinetic energy of the rocket minus the initial kinetic energy of the rocket. And the final kinetic energy of the rocket we're going to assume is zero, because we're going to assume that at escape velocity, the rocket makes it to infinity, but it basically just barely makes it there. So it gets there with essentially no kinetic energy. So in that case, delta K rocket is just minus 1/2 the mass of the rocket times its initial speed squared, which we're calling the escape speed or escape velocity. Okay, so now we're just going to plug this expression for delta K rocket and this expression for delta U grav into our conservation of energy statement. And we get, with some slight rearrangement, that GMEM rocket over the radius of the Earth is equal to 1/2 m rocket times the escape velocity squared. And the escape velocity doesn't depend on the mass of the rocket. That goes away. And what we find is that the escape velocity, the escape, is equal to the square root of 2 times g times the mass of the Earth divided by the radius of the Earth. So that's equal to the square root. I'm going to leave out the units. Everything is in SI units. It's 2 times 6.67 times 10 to the minus 11 times the mass of the Earth is 6 times 10 to the 24 divided by the radius of the Earth, which is 6.4 times 10 to the 6th meters. And if you crunch those numbers in your calculator, what you find out from this simple calculation is that the escape velocity for a rocket leaving the Earth's surface is equal to about 1.1 times 10 to the 4th meters per second, about 11 kilometers per second, which is pretty fast. Well, that calculation is perhaps a little bit too simplistic for our situation where we're trying to get from the Earth to Mars, because not only does the rocket have to move away from the Earth's gravitational pull, it also is subject to the gravitational pull of the sun. So there's a change in potential energy during the trip due to the fact that the rocket is getting further from the sun. So let's calculate that effect and see how it compares to the change in potential energy that is just due to the Earth's gravity. So we just said that the change in gravitational potential energy when the rocket leaves the Earth's surface and moves to some new radial distance, we can write that as g times the mass of the Earth times the mass of the rocket times it's starting off at a distance of 1 Earth radius away from the center of the Earth. And it's ending up at a distance much, much farther. The distance from the Earth to Mars is very, very large compared to the radius of the Earth. So we really don't have to worry about this term. And now let's write down the change in potential energy due to the gravitational effects of the sun on our rocket. So in this case, we're going to have to put the mass of the sun here times the mass of the rocket. And the rocket starts off a distance from the sun of 1 over r, the distance from the sun to the Earth. And in its final stage, its distance from the sun is given by 1 over the distance from the sun to Mars. And the question I want to address is, the calculation we just did just took into account this increase in potential energy that had to take place during the trip. But what about this one? Is this, small, negligibly small compared to this one? Is it comparable or is it bigger? Let's play. You won't know until you plug in the numbers and see the relative sizes of these terms. So let's do it. And as we said, the results at the end, for the escape velocity aren't going to depend on the mass of the rocket. So we could, just set the mass of the rocket equal to anything. It's going to end up canceling out. What we really want to do in comparing these two effects is ignore the factor of the mass of the rocket. We're just going to compare g times the mass of the Earth divided by the radius of the Earth. That's one term. And we're going to compare that to g times the mass of the sun times this term in parentheses here and see which is bigger. So just plugging in everything in SI units here, this factor of g times the mass of the Earth divided by the radius of the Earth squared, the radius of the Earth is 6.4 times 10 to the 6 meters, we get a number of 6 times 10 to the 7th. And that's the number we want to compare to. And what you see right away when you start plugging in numbers is there's sort of two competing effects. The mass of the sun is much greater than the mass of the Earth, 6 orders of magnitude greater. But on the other hand, the distances that we're dealing with from the sun are much greater than the radius of the Earth. So it's a question, it's going to be somewhat close, but let's see which effect wins out. So when we plug all these numbers together, what do we get? You get about 3 times 10 to the 8th. So that's in fact a bigger effect, bigger change when you go from the Earth to Mars, from the surface of the Earth to Mars. The change in potential energy due to the interaction with the sun's gravitational force is actually greater, a bigger effect than the change in potential energy due to the Earth. And we haven't even talked about Mars's gravity in this problem, although that's relatively a small effect because Mars doesn't have much mass. But nonetheless, it shows you that our calculation for the speed that we would need to get to Mars was overly simplistic because it neglected this effect. But don't despair. There's another effect. It seems like we're going to have to make our rocket go even faster. But there's another very important effect which we haven't talked about, and that is the fact that the Earth, of course, is orbiting the sun, and we are zipping along with quite a velocity. We're moving at a speed that is about 100,000 kilometers per hour. So that's greater than the escape speed that we calculated previously. So you're going to take advantage of this. If you're going to get from the Earth to Mars, it's not that you're starting off with zero velocity and you're not going to just try to go straight in this direction. It turns out you want to take advantage of the Earth's orbital velocity and then just change the orbit a little bit and make it to Mars that way. So it takes a little bit longer to get there than if you just tried to go straight. But you'd be crazy to go straight because it would be so inefficient in terms of fuel cost that it would take to get there. So the way people actually get to Mars is to take advantage of the Earth's orbital velocity around the sun and go on a path that looks something like that. So that's it for this worked example. Hope to see you again soon. Bye bye.